do an example of a angular momentum problem here. So we're going to do this problem 10.8. This is a grindstone that's rotating at 2,000 revolutions per minute, requires 50 seconds to stop when its motor is switched off. There's three things they want us to find in this problem. They want to know the angular acceleration of the grindstone, how many radians is it going to turn through before it stops, and how many revolutions is it going to turn through. And I'll just tell you now, we're probably going to do part C before we do part B because our units start out in revolutions and we can wait till the end and do a conversion from revolutions to radians. But let's go ahead and start with part A here and write down everything they want us to find. So we want angular acceleration. That's our question. And what do they give us? They give us that the initial angular velocity is 2,000 revolutions per minute. And it says that it requires 50 seconds to stop. So that's implied, without actually saying it's the final velocity, that our final angular velocity is 0 revolutions per minute. And then they give us a time of 50 seconds. Now you ought to have a red flag right now because we've got minutes here and seconds here. So we're going to want to convert something. At this point, it seems easier to me to just turn the 50 seconds into minutes. So let's just do 50 divided by 60. And that's 0.83 minutes. All right. And that should be pretty much everything we need for this. So if you're thinking back to linear stuff, acceleration is final velocity minus initial velocity divided by time. So the angular version of that would be angular acceleration is angular velocity final minus angular velocity initial divided by time. So we've got 0 revolutions per minute minus 2,000 revolutions per minute divided by 0.83 minutes. And we got 2,000. We'll just go ahead and do this. Negative 2,000 divided by 0.83. And I get that that's equal to negative 2,410. And it's revolutions per minute. So that's revolutions per minute squared. Now, if we're doing significant digits on this thing, we've probably got, loosely, I could say 2 here. It's really only 1 there. So we could say negative 2,400 revolutions per minute squared. We'll go ahead and keep it negative 2,410. This is really more about how to do the problem than dealing with significant digits. So then let's do part B. Again, I said let's skip that. Let's do part C. Through how many revolutions does it turn? So that's revolutions. How many would be like a distance, but it's an angular distance. So the question is, how many turns does it make? All right, so got a couple of formulas to do this. We have a time. So let's look at our linear formulas. Distance would be equal to the initial velocity times the time plus 1/2 AT squared. We could use that one. We've got final angular velocity squared. I'm sorry, VF squared minus V naught squared equals 2AD. So if we were to move that around, we'd get D equals VF squared minus V naught squared over 2A. All right, we can use either one of those. Doesn't really matter, so I'm just going to use this one. We'll convert it to an angular formula. So the angular distance would be equal to the initial angular velocity times time plus 1/2 times the angular acceleration times time squared. So we've got negative 2,000 revolutions per minute times 0.83 minutes plus 1/2 times negative 2,410 revolutions per minute squared times Well, here, I'm going to move this over so we can get this without getting it off the page. Let me restart over here. 2,000 revolutions per minute times 0.83 minutes plus 0.5, we'll make this a little easier, times negative 2,410 revolutions per minute squared times my time squared, 0.83 minutes squared. Okay, let's go ahead and run that through our calculator here. So it's 2,000 times 0.83, that's 1660. And minutes cancel. That's revolutions, and that's good because we want a distance. And then because this term is negative, we're decelerating, this whole thing becomes negative. And remember, this is how many turns it would make if it wasn't speeding up or slowing down. If it were just at a constant rate, we'll end up going less because it's slowing down. So let's go ahead and do this. We're going to have, get that calculator where you can see it, 0.83 squared times 2410 times 0.5. So that's negative 830. And let's look at our units for a second. This is going to end up minutes squared. With minutes squared on the bottom, those are going to cancel, and we end up with revolutions again. And if you do 1660 minus 830, you get 830 revolutions. All right, so kind of a long problem there. We're still not done. We found the angular acceleration, we found the number of revolutions, and then finally we have to go back to part B, which said how many radians is this? So 1 revolution is equal to 2 pi radians. So basically 1 revolution is equal to 6.28 radians. So I'll say 830 revolutions times, I got to get rid of revolutions, so it's 6.28 radians over 1 revolution. Revolutions cancel, and I got 830 times 6.28, I get 5,212. Radians. All right, kind of a long problem there, and made longer by the fact that I needed some room on my paper, but that should get you all the answers to that one.